Hello everyone, welcome to Mathematical Modeling course here at Department of Chemical Engineering, Universitas Gadjah Mada, Indonesia. So in this video, I'm going to show you a demonstration about solving partial differential equation with method of lines using MATLAB. So this is part of the material that has been taught in undergraduate curriculum in Department of Chemical Engineering. So in this problem, we would like to solve tracer flow in a pipe reactor. So this is the description of the problem. An undergraduate student wants to conduct a dispersion study on a laminar flow of pipe reactor with a length of L. So in this experiment, the pipe is continuously flow with water. And the thing is, at a certain time, a specific amount of tracer was injected continuously at the front of the pipe. So tracer is commonly used to diagnose your reactor, how far it deviates from ideal reactors. And the inlet concentration is Ca0, and Ca0 here we have made that it fluctuates according to parabolic equation with time. In addition to that, we have mentioned here that the tracer also undergoes a degradation reaction which follow the second order reactions. If radial dispersion is neglected due to the small diameter of the pipe, so the unsteady state equation that describes the concentration of the tracer in the pipe as a function of distance and time is shown as follow, where we have dc over dt that reflects the accumulation terms of the tracer, and then we have the axial diffusion. Uh, this is reflected as dA times to the d square c over dz squared. This is the second derivative of tracer concentration. And then we also have advective terms reflected by u times d dou c over dou z, and then the reaction terms, which is k times c squared. So I'm not going to explain how we end up with this equation. It could be conducted through taking the volume element and mass balance and volume elements, and finally you will end up with these equations. So in this video, I'm going to focus on how to solve this differential equation using method of lines. In order to solve the differential equations, we need to define what is the initial condition as well as the boundary conditions. For initial condition, we assume that initially the reactor is free from tracer. So we could say that T equal to 0, the concentration of tracer inside reactor is equal to 0. And this is the second order differential equation with respect to axial position. Therefore, we have to define two boundary conditions with respect to Z. And the concentration of the tracer at the inlet of the pipe fluctuates with time following the parabolic function. So at Z equal to 0, Ca0 is equal to Ca0 initial plus 1 over 900 multiplied by 60t minus t squared. This is just parabolic equation that I have made just to have nice figure from this exercise. And z equal to L. At z equal to L, we have common boundary conditions, which is dc over dz is equal to 0. In addition to that, for this simulation, we have data for modeling, and I assume that all units are already consistent in SI units. So really, this number is, I just made it just to make the simulation results later on nice or quite colorful. And the technique that we have here, we're gonna use in this exercise is finite different approximations. So basically, as you all know, guys, that finite different approximation allow us to convert differential equation to algebraic equations. And as you all know that there are three definitions for the first order derivative. We have forward, backward, and center. We have first order error, second order error, and in this course, I only use second order error. For instance, how we define forward, backward later on, which is quite useful in defining the boundary conditions when you have like uh, Neumann boundary condition, for instance, that has differential equation. Then it's nice to use second order error to really minimize the error. And in most of the case, we will use center differential equations for first order derivative, which is will be used a lot in this tutorial later on. In addition to that, uh, most of the time, we need to convert the second order derivative to algebraic equations using this definition that the second order derivative is, the definition is the function at x plus delta x minus 2fx plus fx minus delta x divided by delta x squared. So really this is just to illustrate that in order to find the second order derivative in this point, it depends on the value of the point next to the right and next to the left. And as I mentioned earlier, that we will use method of lines. This is just one of possible method in solving partial differential equations. So method of line is a numerical method to solve partial differential equations among all the possible techniques which use matrix, for instance. And typically, we will use finite difference approximation or FDA to convert the highest order derivative in the PDE equation to algebraic equations. And really, the main machine behind this is we convert one partial differential equation to many ordinary differential equation. This is due to the power of ODE solver in MATLAB. So we all know that ODE solver in MATLAB is probably one of the best solver in the world. It really can solve a huge amount of differential equation in every time step. So I'm going to show you now how it works. Before I move to MATLAB, I'm going to show you the structure of the program that I'm going to use in this demonstration exercise. Uh, so in MATLAB, typically we have to define M files, and what I usually do, I divide the M files into two M files. The one is, I call it a subroutine. This is number two. Uh, the subroutine that I use a lot is to calculate. It is mainly uh, designed to calculate the ordinary differential functions and finite difference approximations. And the subroutine will supply the main program, which is mainly ODE solver. I usually use ODE 15S. And then from this main program, we expect that we could have a plot of concentration as a function of time and position. What I usually do, I plot this in images C, plot in MATLAB to get the trajectory of concentration as a function of position and time. This is just for the sake of illustration. There are many other plot function that is available in MATLAB that you can use in addition to ImageC. This is just to show. So this is how the picture looks like. Okay, and then uh, before I move to MATLAB, so what I'm gonna do, I'm gonna do the first M file to develop the first program, which is program number 2, that really reflects the ODE functions. That's how I usually work. So I make problem number function number 2 first, or this is M file number 2, and after that I'm gonna move the main program, because from my experience, by doing this number 2 first and then number 1, there's no like back and forth many times in showing to the audience in creating MATLAB program. Okay, now I'm gonna move to MATLAB, how it looks like and how it works. So this is the MATLAB environment, as we all know. So this is the common window, but we don't use it a lot right now. We will make a new script, new M file, and as I said, I'm gonna show you how to do the program number 2. This is the function or subroutine that will be used to calculate the ODE functions. And to begin with, we can type function and then n. So this is to show what is that this is subroutine. So in main program, which is not a function, you don't need to put a function. And the output is dc over dt. This will be a vector later on. So we can call this my fun 9D, for instance. This is the way I name it. You can name it differently. It's up to you. And then we need input T and then C. And later on, the rest of the place here, I'm going to use this to send parameters from the main program to the functions. Okay, what I usually do, after I define the functions, I need to provide a place. We call it a pre-allocation to put the results that we expect from this exercise. So this is zeros, and the number of differential equation that we use here is nz. And after we define the pre-allocation, we can say C1 and then C nz plus 1. I usually do this to define the boundary condition that has been described earlier, that C1, that's basically the concentration of tracer at the inlet of the reactor, and that will fluctuate with time. So according to the problem that has been described there, we say the equation Ca0 init plus 1 over 900 times 60 times t minus t to the power of 2. Okay, so that's how the inlet concentration will change with time. We check again one more time if it's correct. It is mentioned here. Yes, this is how it works. And then for at the outlet, the index is at n plus 1, and we can use second order approach. Actually, we can set this equation to 0 because it is mentioned that at z equal to L, the dc over dz is equal to 0. So this is basically 0, and then you can write that the concentration of nz plus 1 as a function of nz and nz minus 1. So what we're going to do, we do it like this, so I can zoom it in. So that's 1 over 3 multiplied by, oops, sorry, that's 4, and then C nz minus nz minus 1, oops, should be nz. This is concentration of nz minus 1. So this is basically dc over dz equal to 0 at z equal to L. because the one at z equal to L, we give it index nz plus 1. All right, I hope you still follow up to this point. And, and now we would like to uh, do the finite different approximation. And this one starts from I from 2 to nz. And then we will define what is the value of the definition of dz over dz. That's and then d square c dz square. This is the second derivative, and then we need to define what is dc dt over I according to the problem that we have explained earlier. So dz over dz, because this index starts from number 2 up to nz, we can use center differential equation for the first order, which is 1 over 2 times dz, right? So, and then we have I plus 1 minus c I minus 1. So this is centered differential equations. We check one more time if this is correct. Yes, and then it is correct. And then for the second order derivative, we will use again the definition of second order derivative is c like I plus 1 minus 2 times ci plus ci minus 1. Okay, this is the second order derivative, and now what we're gonna do, we will show the final equations like what we have in the problem. So dc over dt, that's basically the dA, that's multiplied by dz2 I. This is minus u, this is the advective terms, which is dz over dz I. We have to make sure that the way we name it is consistent or the same as in the previous line. And then we also have the second order reactions here. This is what I like with method of lines. It really shows to us the way we define equation is very similar or the same as like what we wrote in the problem. So this makes it easier, I think, for everyone to solve differential equations in this way. And we make sure again that the dc dt here is consistent, the naming, the indexing, this is nz, dc dz, and so on and so on. Okay, now in order to run this program, we need to supply a number of information from the main program, and we can write everything that we need here. So this is kind of like expedition to send parameters between the two M files. You can also use global, for instance, but I would prefer to use like what I do here. So we define, we need to have nz here. What is nz? We need to have CA0 initial. The time automatically will come. For every time step it will come, so it shouldn't be a problem. And then nz, we already define it, and then we need to define what is dz. And then what else? We need to have dA, we need to have u, we need to have k to run this subroutine. Okay, that's all basically the subroutine that we need to run the method of lines. So I'm gonna zoom out and I'm gonna save this M file. I call it my fun 9D. Okay, now basically we are done with problem. Uh, we are done with the subroutine, and now we can move to the main program. Here is the main program. Uh, let's see how it works. We can make a new M file. This is to show main program. You can write a short description. This is main program for tracer study simulation. And then I usually start with clear all, CLC, close all. This is kind of standard way to begin any main program. And then I usually put my main program in this structure: data, solver, recalculation, and then plotted. This is just to make it easier for me to explain to my students how we should develop our main program. And now we will use ODE solver. In this case, the best ODE solver that we have in MATLAB is ODE 15S. So we can have the output first. This is D and then C. So we'll have a large matrix of C later on. And then you can write ODE 15S. The first place is for the name of the subroutine. Make sure that you put everything in the same folder. The name is my fun 90. And the second place is for T-span. And then the third place is for initial conditions. And then we have empty matrix. That's for option because we don't have any option to define. And then we need to send all parameters that we need, which is NZ, CA0 init, and then yes. So as you see here, the place after option, you can use it to send all informations that you need in main program and in the subroutine. Again, you can use global if you prefer to do so, but I use this way to define my solver. And then the same information can also be copied here. What is NZ? What is 0 in it? What is the DZ? What is DA? What is the U? What is K? And this information mainly we can receive it or we can read it from the problems. It should be given there. And don't forget that we also need the span initial condition as well. It is mentioned that the initial condition is 0 for all position when t is equal to 0. All right, now let's define what is the NZ. As you see here, that the NZ is 100, L is 1, C is 0, init is 0.1. The dA and U is 2 times to the power of 10 times 10 to the power of minus 1. So K is equal to 1, and so on and so on. So we put all this information in our main program. So like we define what is L as equal to 1, and Z is 100, and then CA0 in it is 0.1. dz basically is L divided by NZ. This is the this is for finite different approximation computations. This is to a minus 1. U is I have to double check again. K is equal to 1. U is also to a minus 1. And then we have K is equal to 1, and then T span is in space from 0 to 60, and we divide it into 61 points, so which means it is for every one time unit. So all this information we have supplied from the problems. For initial conditions, this is basically zeros, and then we have 1 times nz. The number of differential equations that we solve for this case is nz. Nz is the number of spacing, the number of points in axial directions. Before we continue, it's better to check if this program works or not. So you can save this. We call it as main program 9D. Okay, and then we can run this program and see how it works. And as you see here, it works very nicely, no error message. And then you can always check the size of matrix C here. As you see here that the matrix C is still 0 for the first column. This is something that we need to correct later on. And then the length is up to 100, and we still need one more data, which is at nz plus 1, which is 101 here. That's the value that we will calculate in recalculation step. And to do this, we will copy this information and then paste it to the main program. So this is the place where we're gonna correct the value of the first column and then the last column. And since this is column-wise operations, we will put double dot there. The t here, we will see if the t works or not. I think it should work because the t, if you check it again, in the command window, we will have t here. So this is the value of t, which is exactly the same like t span. So it shouldn't be a problem when you write just t like that. So this will create a vector. And then similarly for nz plus 1, we need to do element-wise or column-wise operation. And this could be conducted like this. Okay, so by doing this, basically we correct the value of all elements in the first column and all elements in the last column. So when we have done this, it's time now for plotting all results. There are several functions that is available to do this, but I prefer to use images C. And we define what is the x-axis. The x-axis here is the axial position, which can be defined as line space 0 to L, and then you divide it with nz plus 1 points. So the y-axis is the t-span, basically, and then you can have images C, images. This is the contour, and then x-axis, y-axis, and then C. Alright, then what happened here, it will generate like contour plot, like showing the dynamic of concentration as a function of position and time. And I usually put grid on, and then I put x label like axial position. That's basically what's x-axis described, and then we have time span in y label. And then we need to, I usually put color map. It is jet because the new version of MATLAB, it gives like yellowish color. That's something that I'm not used to. I'm not that familiar. I prefer to have jet color map. And then I put usually color bar. So that's to show like scale of the concentration. Okay, now we can minimize this and we try to run this program. It seems like there's error. Oh, not really. It works. Okay, so this is basically how the simulation results look like. Uh, as you see here, uh, the y-axis here, it shows the time span. So initially it is blue. Blue means 0. The reactor has no tracer. And then we, at certain time, start from 0, we start to inject Ca0. Ca0 follows parabolic equations according to the time. And then we have like parabolic profile uh, in the inlet. And what happened then, this this tracer will be distributed by diffusion and advection, and we will have the distribution of tracer in all reactor as a function of time, and the L is here is from 0 to 1. Okay, uh, so that's all basically for the first task here, how to do simulation, and I hope you enjoy it and you can learn how to solve partial differential equation with method of lines. So thank you.